In this video, we are going to learn the difference between functions that are written implicitly and functions that are written explicitly. Then, once we're able to tell the difference, we will then be able to differentiate implicit functions. So getting started, first let's talk about the difference between implicit and explicit functions. Example, the equation y is equal to -5 divided by x is written explicitly because it tells us explicitly what y is. It is -5 divided by x. On the other hand, the equation xy is equal to -5 is the exact same equation. All we did was multiply both sides of the equation by x, but this is not written explicitly because it does not tell us exactly what y is equal to. In other words, equations are written explicitly when they are particularly solved for y. So these are all solved for y explicitly. These equations over here say the same thing, but they say it in a different way. So for another example right here, the function y is equal to 1 over x could be written implicitly as the equation xy is equal to 1. So let's say that we had started with the equation xy is equal to 1, and I ask you to find y prime. So if we had this equation and we want to find y prime, we would probably start off by solving for y. So I would take both sides of this equation and I would divide both sides of this equation by x. And I would get that y is equal to 1 over x. If I'm trying to take the derivative of that, I probably don't want to write it in this form. I would rewrite it as x to the -1, because then I could use the power rule to take the derivative of x to the -1. I would bring down the exponent of -1, and my new exponent would be -2, leaving me with -1 over x squared. So far, we've seen an example where we started with an equation written implicitly. We were able to solve for y and write it explicitly and then apply derivative rules that we already know. But what if we started with an equation like this? This is certainly written implicitly because that is not solved for y. Furthermore, it is difficult to solve for y in that equation. So how would we find the derivative? How would we find dy dx if we have something where it's difficult to solve for y? Well, the way that we would do that is that we would take the derivative implicitly. When we are taking the derivative implicitly, we have to remember that y is a function of x and that the chain rule must be applied. Let's look at some examples. In example 1a, we want the derivative of 2x to the 4th. Notice that on the inside of this here, what we're taking the derivative of, there is no y. This is how we are used to taking derivatives, right? Because usually one side of the equation only has x's. We have already spent a lot of time in this course talking about how to take derivatives of things like this, where there's only x's on one side. So this is no different than a basic derivative problem. I would bring down the exponent of 4. I would ultimately end up multiplying it with the 2 to give us 8x to the 3rd. On the other hand, example 1b has a y on the inside. And in fact, I am missing my ddx. I'll have it on there by the time you all get this. But if we want to take the derivative of y to the 5th, the power rule still applies. We still bring down the exponent of 5. The new exponent on y is now 4, but we have to do the chain rule because this is not x, it's y. And the chain rule tells us that we have to multiply by the derivative of y. Well, the derivative of y is just dy dx. So what was the difference between example A and example B? Well, in example A, we had an x right there. So in essence, what we did in example A is when we brought down this exponent of 4, multiplied it with that 2 to give us an 8, decreased our exponent to 3, we still did the chain rule. Because what was on the inside here was x. We come in and we multiply by the derivative of x. But the derivative of x is just 1. And so that doesn't change anything. This is still just 8x to the third. So I never even really have to come in and do this orange part when this is just x. But if this is not x, then when I come in and do the chain rule, this will not be 1. It will be something else. In this case, it was dy dx. So that's the difference between taking the derivative implicitly and taking the derivative explicitly. Let's look at some more examples. In example C, I'm going to come in and take the derivative of each term. I will go ahead and write these out. We haven't been doing it for a while because we're getting more used to taking derivatives, but I will come in and take the derivative of each of these terms. The first term is a basic power rule. It is just simply x on the inside. I'm taking the derivative with respect to x. So I just treat it normally, bring the exponent of 2 down, the new exponent on x is 1. The second one, we do have that constant of 8 that can come out in front. So I'll just go ahead and pull that 8 out. And we would be left with taking the derivative of just y with respect to x. But the derivative of y with respect to x is dy dx, or y prime. That's our answer there. I'll point out that notationally it's not incorrect to write this because dy dx and y prime mean the same thing. Those two things are exactly the same. I think it's better to write dy dx when you're doing implicit differentiation because I think in some problems this y prime can look a little bit too much like y, and that would throw you off. Let's look at example D. What we're trying to take the derivative of on the inside here is in fact a product, and so we will start off with the product rule. I'm going to need to identify what f is and what g is. F will be the first factor of x squared, and g will be the second factor of y squared. We're going to need f prime and we're going to need g prime. F prime, taking the derivative of x squared with respect to x, is simply going to be 2x. G prime, taking the derivative of y squared with respect to y, I'll bring down the exponent of 2. The new exponent on y is just 1, and then I have to multiply by the derivative of y, which is dy dx. So now I am ready to do f prime g plus g prime f, because that's what the product rule is. F prime multiplied by g, and then we will add g prime multiplied by f. And this is our derivative. So something to notice about all 4 of these examples is that every time we took the derivative with respect to x of something that involved a y, every time we took a derivative of something that involved a y, we picked up a dy dx. So now we are going to look at how to determine dy dx for an equation that is defined implicitly. So far we have not worked with any equations. We took the derivative of expressions that had either only x in them or x and y in them. Now we're going to be working with an equation that is defined implicitly and finding dy dx for them. There are 4 steps that are outlined here. We're going to begin with the first step that tells us to differentiate both sides of the equation with respect to x. So we are going to go into every term in this equation and we are going to apply our derivative operator. So now that we have completed step 1, well actually we haven't completed it. So now I'm going to come in and start taking the derivative. In my first term, the derivative of x to the 4th is 4x to the 3rd. In the second term, to take the derivative of xy, we are going to need to use the product rule because we have a product of x multiplied by y. So I'm going to do a quick product rule here where f is x and g is y. So our f prime is 1 and our g prime is dy dx. The derivative of y is dy dx. Notice that there is a minus sign in front of this. Product rule tells us that we need to do f prime g plus g prime f. I'll go ahead and simplify that. F prime multiplied by g would be 1 times y, which is just y. And then I'm going to add g prime multiplied by f. So that's me adding dy dx multiplied by this x here. So I'm adding x dy dx. So this is what we get for the derivative of xy. And please do note that it all needs to be subtracted because there's that minus sign in front of that. So we have a minus y minus x dy dx. Now moving on to taking the derivative of y to the fifth. Bring the exponent of 5 down. The new exponent on y is 4. Chain rule tells us the derivative of y is dy dx. Have an equal sign, and the derivative of 7 is 0. So now we have completed the first step and taken the derivative of both sides of the equation. Now we are going to gather all the terms involving dy dx and move them to the left side of the equation and everything else to the right side. It doesn't really matter what side you put it on. I just put left and right so we can kind of stay consistent. So this term has a dy dx and this term has a dy dx. So I'm going to keep these two terms and their signs on this side of the equation, and I'm going to move the other two terms. So I'm going to subtract 4x cubed from both sides, and I'm going to add y to both sides. So my new equation is now going to be negative x dy dx plus 5y to the fourth dy dx. Everything that was on the left side that had a dy dx stayed. And the two terms that ended up on the right side are negative 4x cubed plus y. So now we have completed the second step. We've moved things around so that all the dy dx terms are on the same side. And now that they're on the same side, we can factor a dy dx out from that side. So I'm not doing anything to the other side of the equation. All this stuff here stayed the same. But the two terms on the left side that have the dy dx can be factored out. And let's see what that's going to leave us with on the inside of the parentheses. From the first term, it leaves us with a negative x. And from the second term, it leaves us with a positive 5y to the fourth. So we've factored out that dy dx, and we're trying to solve for this. So the last thing we need to do is divide both sides of this equation by everything that's in these parentheses right here so that it'll cancel out. So coming in and dividing both sides of this equation by negative x plus 5y to the fourth leaves us with dy dx is equal to negative 4x cubed plus y minus x plus 5y to the fourth. In example 3, we are being asked to determine the slope of the graph given by this equation at the point 3, 1. First thing we have to do is be able to decipher that when this says determine the slope of the graph, that means the exact same thing as find, or rather evaluate, the derivative, which is dy dx, at the point that they gave us, 3, 1. So a better way to say it is at x equal to 3 and y equal to 1. So now that we know what we need to do, we need to first find dy dx, and then we will plug in 3 and 1. So we're going to begin by taking the derivative implicitly. So we need to apply the derivative operator to each term in this equation. There's only one term on the left side and one term on the right side. I'll begin by taking the derivative on the left side. We do have this constant here. We have that 3, so that's not going to matter too much. This power rule will start in here. General power rule. We have this exponent of 2 that's going to come down and get multiplied with that 3 to give us a 6. The inside of the parentheses will stay the same, x squared plus y squared. The exponent of 2 will drop down to 1. And the chain rule tells us that we then need to come in and multiply by the derivative of what's on the inside, which was x squared plus y squared. On the other side of the equation, we're taking the derivative of 100xy. This is a product, so I'm going to do a product rule over here and say that f is the first factor of 100x and g is the second factor of y. F prime would then be 100, and the derivative of y is dy dx. Product rule tells us we need to look at f prime g plus g prime f. F prime is 100, which we will multiply by g, which is y. To that, we will add g prime f. So that is dy dx being multiplied by 100x, giving us 100x dy dx. Now we need to go back to the left side of the equation. I don't need that 1 there because we still have to take this derivative here. I'll bring down everything else we have. We'll take this derivative term by term. The derivative of the first term, x squared, is 2x. And the derivative of the second term, y squared, is 2y, but because there's a y there, chain rule tells us to multiply by the derivative of y, which is dy dx. And I'll bring down everything we had on the right side of the equation. So at this point, to solve for dy dx, we would need to do some FOILing out here. This is be very algebra intensive, but I don't actually have to solve for dy dx. I just want to know what is the value of dy dx when x is 3 and y is 1. I have finished differentiating this expression. So we are now able to simply plug in x is equal to 3 and y is equal to 1. So I am coming into this equation and I am replacing all of the x's with 3 and all of the y's with 1. And what I want to know now is, well, what does dy dx equal? So to get from here to here, now I'm going to solve for dy dx. Is dy dx is equal to 13 over 9. In example 4, we have an equation that is defined implicitly because it's not explicitly solved for y, and we want to find dy dx. So we're going to begin with step 1 of implicit differentiation, and we're going to take the derivative of each side of the equation. On the left side of the equation, the derivative of cosecant is negative cosecant x cotangent x. On the right side of the equation, we want to take the derivative of a product, and so I am going to apply the product rule, where f is the first factor of x and g is the second factor of 1 plus cotangent y. We're going to need f prime and g prime. F prime, the derivative of x, is 1, and g prime, the derivative of 1 is 0, and the derivative of cotangent is negative cosecant squared y. But because there's a y on the inside, chain rule tells us that we are going to pick up a dy dx because it was not just x on the inside. So when you're taking this derivative here of this cotangent y, how we get this is that, remember in 2.4 from the chain rule, we had a rule that told us how to take the derivative of these trig functions if they're composed with other functions. So for instance, this version here, in our case, our u was y. We're trying to take the derivative of cotangent y. So we should get negative cosecant squared y, but then this needs to be multiplied by u prime, the derivative of what u was. Our u was y. The derivative of y is dy dx. And so that is how we're getting what we have here. So back to our product rule. We're now going to be filling out f prime g. And to that we are going to add g prime f. So I'm going to take this negative x and multiply it with that negative cosecant squared y. That will change this to a minus sign. And there's still that dy dx on the end. And that dy dx is what we are trying to solve for. This is the point where the steps tell us to get the term that has dy dx on the left side of the equation by itself. So it doesn't matter if you put them on the left or the right. I'm going to stick to what it says. I'm going to move this term to the other side because it has dy dx. But this term does not have dy dx, and so I'm going to move that to the other side. So now that I have my term with dy dx on the left side, the next step was to factor it out. That's not really necessary here because there's only one term on the left side. Technically, it would just give you this, which is really just rewriting that left side of the equation. And then finally, the last thing that we would do is we would come into both sides of the equation and we would divide by what's inside those parentheses. Because when I come in and I divide both sides by this x cosecant squared y, this cancels out and we are left with what dy dx is equal to, which gives us our final answer. We begin by taking the derivative of both sides of the equation, and so we are taking the derivative of each term. So now I'm actually going to come in and start to take the derivative. The derivative of secant is secant tangent, but we have a pi x on the inside, and so we would have to use the chain rule. The derivative of pi x is just pi, and from the secant part, the derivative of secant is secant tangent. So we have a secant pi x and a tangent pi x. Because remember, this inside should stay the same on both of those. The derivative of tangent is secant squared. So we will pick up a plus secant squared from this second term. And remember, chain rule says the inside should stay the same. So we still have a pi over 2 y on the inside. But notice that I did leave a space here because chain rule says I'm going to have to come over here and multiply by whatever the derivative of that is. Well, remember that y has a derivative, and the derivative of y is dy dx. And it does have this constant of pi over 2 in front. So we will have a pi over 2 dy dx. So this pi over 2 dy dx came from chain ruling the derivative of that pi over 2 y. On the right-hand side of the equation, the derivative of x is 1, and the derivative of y is dy dx. So now that we have taken the derivative of each term in the equation, we are going to gather the terms that have dy dx on the same side of the equation. So those are our two terms. I'm going to put them both on the left side. So to both sides of the equation, I am going to add dy dx so that I can move this from that side to this side. And we are also going to subtract this first term since it does not have a dy dx, so it'll cancel out and no longer be on the left side of the equation. So what we are left with on the left side are these two terms, both with dy dx. And on the right side of the equation, we have this 1 minus that term. Now we are going to factor the dy dx out from the terms that have dy dx. So nothing's going to be changing on the other side of the equation at this moment. First term, we are left with everything there except for that dy dx that got factored out. And then when we factor dy dx out from the second term, we are just left with a 1. When you factor something out from itself, it leaves you with a 1. So now to solve for dy dx, we're going to come in and divide both sides of this equation by what we have in parentheses, because this will isolate the dy dx that we factored out once we come in and divide by this on both sides, leaving us with our final answer. In our next example, we want to find the exact value of the derivative at the given point. So we're given an equation that is not defined explicitly, that is defined implicitly, and then we are given an x value and a y value, a point. So we need to find dy dx, and then we need to plug in x is -2 and y is 6. Oh, excuse me, pi over 6. Okay, so first, to find dy dx, we're going to have to use implicit differentiation. So we're going to begin and take the derivative on the left side of the equation and the right side. On the left side, on the inside here of the derivative operator, what we're taking the derivative of is a product. It is a product of x squared and cosecant y. And so we are going to have to use the product rule in order to take that derivative, where f will be x squared and g will be cosecant y. Taking f prime, we get 2x, and taking g prime, we get negative dy dx, cosecant y, cotangent y. So where did that come from? Well, let's go back and look at what the derivative for cosecant is. So back in section 2.3, we learned that the derivative for cosecant x is negative cosecant x cotangent x. But that's cosecant x. We don't have cosecant x. We were taking the derivative of cosecant y. So we learned in section 2.4 that if it's not x on the inside, if it's some other function, say of u, the derivative is still negative cosecant cotangent, but you also pick up this u prime on the outside. And so that is where we get this dy dx from, because we still have the negative cosecant cotangent, but we also need to multiply by the derivative of y. So now I'm actually going to apply the product rule, which is f prime multiplied by g. So we have 2x multiplied by cosecant y, and then to that we are adding g prime multiplied by f, but g prime is negative, so it'll be subtracted, a negative x squared dy dx cosecant y cotangent y. So that takes care of the derivative on the left side. Now we need the derivative on the right side, which is going to be pretty easy because the derivative of 8 is simply 0 because 8 is a constant. Now I want to get my terms with dy dx on the same side. I only have one term with dy dx, so this term is going to be moved over to the other side of the equation. I'm going to subtract it from both sides. That way we'll only be left with the dy dx term on the left side. And when we subtract that over here from 0, it'll become negative. When we subtract this term on both sides of the equation. And now, typically is when we factor dy dx out, but because there's only one term here, I don't have to factor it out. I can see the dy dx that we want to solve for, And to get it by itself, we need to divide by everything else that's around it. So we're dividing both sides by negative x squared, cosecant y, cotangent y. So dividing both sides by this cancels all of this out and leaves us with our answer for dy dx. But this can simplify. We have a cosecant y in the top and the bottom that we can cancel out. And then we have an x over an x squared, so we can cancel one of those x's out. We also have a negative over a negative, so the negatives can cancel out. And then finally, the last thing I'll do to simplify this is I'll rewrite the cotangent y in the denominator as a tangent y. So now that we have dy dx, I'm going to evaluate it at the point that we were given. One way to denote that is we put a vertical bar and we write the point that we are evaluating it at. This indicates that we're going to plug in x is equal to, we already wrote that. We're going to plug these in. So in dy dx, I will be replacing y with pi over 6. And in the denominator, I'll be replacing x with negative 2. And now when I simplify this, the 2 and the negative 2 will cancel and simply leave me with a negative. And the tangent pi over 6 is equal to root 3 over 3. And so our final answer is the negative square root of 3 divided by 3. In our final example, we are asked to find the slope of the tangent line. Slope of the tangent line automatically means find the derivative, because that's what the derivative is, to the equation at the given point. So we're given an equation that is again defined implicitly, because it doesn't simply say y equals blah, blah, blah. And we're given an x value and a y value. So we're once again going to get started by taking the derivative of both sides of this equation. On the left side of the equation, we take the derivative beginning with the general power rule because we have something raised to a power on the inside. So we begin by bringing down our exponent of 2. The exponent on the x squared plus y squared is now 1. And chain rule tells us that we have to multiply by the derivative of whatever x squared plus y squared is. On the right side of the equation, in order to take the derivative of 4x squared y, we are going to need to use the product rule because we have 4x squared being multiplied by y. Taking f prime and g prime, we can then use the product rule to get f prime multiplied by g and add g prime multiplied by f. We need to finish taking the derivative on the left side because we have this derivative of this x squared y squared. The derivative of x squared is 2x, and the derivative of y squared is 2y, dy dx. This is the point where we would get all the terms with dy dx on one side of the equation and then factor it out. But we don't actually have to solve for dy dx at this point. Similarly, we didn't have to solve for dy dx at this point in this equation. Once you have finished taking the derivative, if all you're being asked to do is to find the value of the derivative at a point, you can go ahead and plug that point in here. So what I'm saying is we don't have to finish solving this for dy dx right now. We can go ahead and plug in x equal 1 and y equal 1, which will make the equation a lot simpler, and then we can find dy dx. So when x is equal to 1 and y is equal to 1, this equation becomes 2 times plugging in 1 for x and y there, gives us 2. Plugging in 1 for x and y in the third factor here would give us 2 plus 2 dy dx. Going on to the right side of the equation, replacing x and y with 1, we have 8 plus 4 dy dx. And now it will be a lot easier for us to solve for dy dx. I would like to point out that I didn't do this in the last example because people might not want to evaluate cotangent and cosecant at pi over 6. I'm sure you can. You learn that in trig, but it might be a little bit easier to simplify this and then just plug in here. Either way, you could have done it for any of these problems when you're looking for the derivative at a certain point. So now I'm going to continue to simplify this so we can solve for dy dx. So now I'm going to subtract 4 dy dx from both sides of this equation, which leaves me with 4 dy dx is equal to 0. And then dividing both sides by 4, I get that dy dx is equal to 0. So this graph must have a horizontal tangent line at the point 1, 1.